In this video, we are going to discuss how to calculate tension in the string for an object swung in vertical circle. The question says, a billiard ball of mass m equals 0.150 kilogram is attached to a light string that is 0.50 meters long and is swung in a vertical circle of radius 0.50 meter. If the ball is traveling at 3 meters per second at the bottom of the vertical circular path, what is the tension in the string at that moment? Include a free body diagram as a part of your solution. So let us first discuss this part of the question, then we will go to the next part. So here you have a billiard ball of mass m equals 0.150 kilogram, and it is swung in a vertical circle with the help of a light string that is 0.50 meter long, which is also equal to the radius of the circle. The speed of the ball at the bottom of the circle is 3 meter per second, and we need to find the tension in the string at this position. So let us first draw all the forces acting on the ball when it is at the bottom of the circle. First, we have the force due to gravity Fg, which acts vertically down. This is the speed of the ball, the tangential speed, which is 3 meter per second. Then you have the tension in the string acting towards the suspension point. I will call this as T. I need to find the value of this tension. So we will write the equation of net force. If we choose our vertical axis to be y, so I can write F net y to be the vector sum of all forces along y-axis. When we say vector sum, we have to take the direction into consideration. And by convention, any force which is going up, we will take them positive, and the ones going down, we will take them negative. So I get F net y as T minus Fg. Now this net force along y-axis is giving the ball the required centripetal force to move along the circular path. And the centripetal force at any position always points towards the center of the circle. So at the bottom point here, it is going along positive y-axis. So we can write F net y to be equal to positive Fc equals T minus Fg. I want to find the tension in the string. So we get tension in the string T to be equal to Fc plus Fg. Centripetal force is given as mv squared over r, and Fg is m times g. So let's substitute their values to calculate the tension T. Mass m, we can take it out as common. So we write this as m v squared over r plus g. M is 0.15, v is 3 squared, r is 0.5, and g is 9.81. And when you solve this, you get tension at the bottom of the string to be equal to 4.17 Newton. The next part of the question says, the string can handle a maximum tension force of 10 Newton before it breaks. What is the maximum speed the ball can have at the bottom of its path before the string breaks? So here the question says that if the maximum tension the string can handle is T equals 10 Newton, so what maximum speed can it have at the bottom before the string breaks? So again, we are going to use the equation of net force to calculate the maximum speed. We know from equation of net force, centripetal force Fc can be given as T minus Fg. We know that centripetal force is mv squared over r, that is equal to T minus Fg, which is m into g. We can find v by rearranging the terms. So we write v squared equals, multiply with r and divide with m. So r times T minus mg over m. That will give me v equals square root r T minus mg over m. Now substitute, v will be equal to square root R is 0.5, maximum tension is 10 Newton, minus M is 0.15, G is 9.81 over 0.15. So the maximum speed ball can have before the string breaks is 5.33 meter per second. So here you can use equation of net force to either find the tension in the string or the centripetal force. And once you've found the centripetal force, you can use that to find either the speed of the object or the centripetal acceleration. Because we know centripetal acceleration is nothing but AC equals V squared over R. Or you can also find this as FC equals M times AC, where AC will be equal to FC over M, where Fc is centripetal force and m will be the mass of the object. Part B of the question says, if the ball is traveling at 3 meters per second at the top of the vertical circular path, what is the tension in the string at that moment? Include a free body diagram as a part of your solution. So here we need to repeat the same steps, but this time we will find the tension at the top of the circular path. So let us first draw the free body diagram. You have the first force, which is force due to gravity, Fg, acting vertically down. Then you have the tension in the string pointing towards the suspension point, which will also act vertically down. Let us choose the vertical axis to be our y-axis. So I can write net force along y-axis to be equal to. Now net force along y-axis is nothing but the vector sum of all forces along y-axis. There are two forces here, Fg and tension T. Both of them are pointing down. So I can write F net along y to be equal to negative Fg and negative T. Now this net force is also the force which is responsible to provide the ball with the required centripetal force to keep moving along the circular path. And centripetal force always points towards the center of the circle, which for this position is pointing down towards the center. So I can write F net y to be equal to negative Fc. Negative sign only because at this position it is pointing towards the center, which is down. So we get this as negative Fc equals negative Fg minus T. We can cancel off the negative sign here as it is present in each term. So we get Fc to be equal to Fg plus T. I want to find the tension in the string, so we can move Fg to the other side. I get tension T as Fc minus Fg. Fc we can write as mv squared over r and Fg as m into g. Take m common. We get this as v squared over r minus g. Now substitute to find the tension. Mass m is 0.15. V is 3 squared over r, which is 0.5 minus 9.81. And when you solve this, you get the tension at the top to be equal to 1.23 Newton. Next part C. If the ball is traveling at 3 meters per second, at the moment when the string makes an angle of 45 degrees from the vertical, as shown, calculate the tension in the string. So now the ball is at this position, making an angle theta of 45 degrees with the vertical. And we need to find the tension in the string here. So again, let us first draw a free body diagram to show all the forces acting on the ball. So first we have the force due to gravity Fg. This vector here is the tangential velocity v. After Fg, we have the tension in the string T. I will call this T, pointing towards the suspension point. Now, since the radius vector is making an angle theta with the vertical here, to simplify our problem, we will choose the coordinate axis such that the y-axis lies along the radius vector, that is along the tension in the string. So I can write this as my y-axis. And the x-axis will be an axis perpendicular to it. So this is x. Then from the figure, we can see that tension T is along the y-axis. But force due to gravity lies neither on the x-axis nor on the y-axis, and it makes an angle theta with the y-axis. So we can split Fg into its component. One component that goes along the y-axis, we will call it Fgy, and the other component that goes along the x-axis, we will call it Fgx. We need to find the tension in the string, and tension lies along the y-axis, so we will discuss equation of net force along y-axis. Along y-axis, I will write F net y as vector sum of all forces that goes along y-axis. Here you have two forces. First, you have the tension in the string, and then you have Fgy. So I can write this as T minus Fgy. If we take this direction to be positive and this to be negative, same for the x-axis, this is positive and here it is negative. So F net y will be equal to T minus Fgy, where Fgy is nothing but Fg cosine theta, as it is the side which is adjacent to the angle theta. So I can write this as m times g cosine theta. Now this net force along y-axis is also the force which is responsible for keeping the ball along the circular path. So it is giving the ball the required centripetal force to move along the circular path. And we know centripetal force always points towards the center of the circle, which for this position points towards positive y-axis. So I will write F net y to be equal to positive Fc, which is equal to T minus Fgy. I want to find tension in the string, so I will write T to be equal to Fc plus Fgy. We move Fgy to the other side. Now let's substitute their values. Fc is mv squared over r plus Fgy is mg cosine theta. Take m as common and you get T equals m v squared over r plus g cosine theta. Now substitute. T will be m is 0.15, v is 3 squared, r is 0.5, g is 9.81, cosine of the angle 45. And when you solve this, you get tension in the string to be equal to 3.74 Newton. So anytime you have a problem where you need to find tension in the string at an angle theta with respect to the vertical, always try to choose your y-axis or any one of the axes along the line containing the tension force and split force due to gravity. Because if I chose my vertical to be along the force due to gravity, I would have to split two forces, the tension and the centripetal force. So to make your problem easier, it is better to choose one of the axes along the line of tension and centripetal force so that you only have to split force due to gravity. Another important thing this kind of question can ask you is to find the magnitude of linear acceleration as well as centripetal acceleration. Now, linear acceleration is nothing but the tangential acceleration. And tangential acceleration will be generated by tangential force, and which in this case is Fgx. How do you determine which one is a tangential force? Just look at the vector or any component of force which is along the tangent to the circle. So here my tangential force is Fgx. So Fgx will give me my tangential acceleration. We know force is mass times acceleration. So I can find A as Fgx over m. Fgx is the side which is opposite to angle theta. So Fgx you can find as mg sine theta. So here when you substitute that, you get mg sine theta over m. So tangential acceleration will be equal to g sine theta. Now this value can change with the problem. The key to remember how to find tangential acceleration is to look at all the forces which is along the tangent to the circle. Only the forces, not the velocity vector. We have two vectors here along x-axis, but only one force. I don't include velocity vector in equation of forces. So since I had only one force here, I will take my net force along x-axis to be Fgx and then find acceleration by using the basic definition of force. The same thing you can do to find centripetal acceleration. By using the equation of net force along y-axis, we found centripetal force to be equal to this. Once you know centripetal force Fc, you can find acceleration by using the definition Fc equals m times ac, and ac will be equal to Fc over m. So whatever Fc you have here, t minus Fgy, you can find acceleration by dividing it with mass m.